Okay, today we're going to talk about momentum and collisions. So let's go through the first what do you think questions. So two skaters have equal mass and are at rest. They are pushing away from each other as shown. Compare the forces on the two girls. So if they have equal mass, their forces should be equal to each other. If they're, well, I guess it does say equal mass. And so the forces would be the same and their velocities would be the same, right? If the one on the right had greater mass, she'd be able to push with more force, moving this one a little faster. And then how would your answers change if the girl on the right was moving towards her friend before they started pushing apart? Okay, think about those as we go through this. So, we're looking at collisions. So when bumper cars collide, our force 1 is equal to the negative force 2 because they're moving in opposite directions. And so their impulse, since they're in contact with each other for the same time period, their impulses are the same. And so we can also say that the change in momentum is equal to each other. So the change in momentum of one object is equal and opposite to the change in momentum for the other object. So the total momentum is neither gained nor lost in the collision. So the momentum of this system, of the first bumper car and the second bumper car added together, is equal to the first and second bumper car momentum after the collision. So you're looking at total momentum of both cars, the whole system. So the momentum P1 is what would be like the momentum before the collision, and then P2 is the momentum afterwards. Here's our law of conservation of momentum, and the reason why these are bolded, the velocities are bolded, is because the mass of the two objects usually does not change. So the mass before the collision doesn't change, but the speeds before and after will change. So you can M1 is equal to M1 on this side, M2 is equal to M2. So the total momentum remains constant during the collision. The momentum lost by one object equals the momentum gained by the other object. And so this is the conservation of momentum. So let's watch what we have here.
In the absence of friction or any other external forces, the total momentum of a system of objects interacting with one another remains constant, regardless of the nature of the forces between the objects. When two skaters, originally at rest, push each other away, in the absence of friction there are only internal forces acting on them, so the total momentum of the two is conserved. As they move apart, the skaters have momentum that is equal in magnitude but opposite in direction. Therefore, their momentum has opposite sign, and the total momentum is equal to 0, just as when they were at rest.
Okay, so we would still have, so before the collision, oh shoot, let me get a different color so you can see it a little better. So before the collision, we have M1 V1 is plus M2 V2. And since they are both at rest, it was equal to 0. Now, since we have M1V, you know what? I'm going to put a little initial, and then that way we can put V1F for final, plus M2V2F. Now, this case, this is a positive velocity, this is a negative velocity, so that's why this is going to be a 0. This is negative velocity because it's in the opposite direction. Remember, velocities are a vector, they're not scalar, so you do have to take into account direction, and that will affect this. So if a 62 kilogram astronaut on a spacewalk tosses a 0.145 kilogram baseball at 26.0 meters per second out into space, with what speed does the astronaut recoil? So we're going to look at, we have the mass of the astronaut and the velocity of the astronaut initially, plus the mass of the ball and the velocity of the ball initially. It's going to be equal to the mass of the astronaut times the speed of the astronaut final, plus the mass of the ball times the velocity of the ball final. So initially, their initial speeds are both going to be 0. So we have 62.0. This should make this side all equal to 0, but let's write out our numbers so we can see that. Plus 0.145 times 0. Okay, we're going to have mass of the astronaut 62. So I have 62 kilograms times, we're looking for the astronaut's final speed, so let's leave that as a variable, plus the mass of the ball is 0.145 kilograms. And then we'll have 26 meters per second is the speed of the ball final. So when we take, we're going to subtract the 0.145 subtracted over times 26 is equal to 3.77. So we're going to have a negative 3.77, okay, because we took the 0.145 times 26 is 3.77, and that would be newtons, right? No, kilogram meters per second. And so we're subtracting over, so we can have a negative, we have a negative value. Now we're going to divide by 62, and we get, I have 0.0608, and it would be negative. Oops. 0.0608. Our kilograms would cancel out, and we're left with meters per second. So does that make sense that the larger object would have a lot smaller speed because it's harder to change its momentum, harder to change its velocity. And it's negative because it's in the opposite direction of the ball. So we found the initial, yes, substitute V. Yes, we got the right answer. Good. Would a pitcher recoil backwards? No, not like the astronaut, because we're looking at systems without friction, and so friction is what holds the pitcher to the pitching mound. Okay, so now we've gone through these, and you should be able to answer those questions again. Oops. So then collisions are sometimes described as elastic or inelastic. To the right is a list of colliding objects. Rank them from the most elastic to inelastic. So what factors do you think you'll consider? So think about that. Elastic or inelastic? Take a little time and look at those, discuss them. Okay, let's go through these. So perfectly inelastic, where when two objects collide and stick together, like the two football players, a meteorite striking the earth, the bullet hitting the block. Momentum is conserved. The masses would combine after the collision, the masses combine, and we have this. So we really did an example of this already when we did the mass of the two football players combining. So a 2 times 10 to the 5th kilogram train car is moving east at 21 meters per second and collides with this fully loaded train car at rest. So on the left side, initially the only momentum we have is the 2 times 10 to the 5th railroad car, because the other railroad car is at rest. So that would be 0. So I'm just going to write out this. And east I'm going to make positive. just in case we get a negative, that would mean west. So this would equal the two cars stick together. So we have the mass of the two cars is 2 times 10 to the 5th plus 4 times 10 to the 5th. And then we would have a new velocity. So let's calculate that V. I get a positive 7. So that would be 7 meters per second east, since we've made east positive and west was negative. Let's check our answer. Yes, we were right. Now calculate the kinetic energy of the two cars before and after the collision. Was kinetic energy conserved? Well, what was the kinetic energy? We have our equation, 1/2 mv squared. So initially we can find the energy and the final energy also, and the energy is not conserved. Why is that? Right, there's loss of energy, there's thermal, sound, all those energies that can be lost. So we don't have a closed system, so we can lose some energy here. Kinetic energy is less after the collision. It's converted into other forms of energy. So yeah, internal energy or the thermal energy, sound energy. Some kinetic energy may remain after the collision, or it may all be lost. Okay, elastic collisions were when objects collide and return to their original shape. The kinetic energy remains the same after the collision. So perfectly elastic collisions satisfy both conservation laws, both the conservation of momentum and the conservation of energy, whereas the inelastic only conserve momentum. So two billiard balls collide head-on as shown. Which of the following possible final velocities satisfy the law of conservation of momentum? Oh, all three. Whoops, I didn't mean to go off through that. But as long as the mass, well, our mass times velocity, this second one has no momentum, so we'd have this. As long as the velocity would equal the 0.35 times 4, which is 1.4, as long as the mass times 2 and the mass times 2 were to give you 1.4, then you would have conservation of momentum. Now, which one satisfies the law of conservation of kinetic energy? So beforehand, we have 1/2 times the mass times velocity squared. Shoot, I forgot to square it. .8 is the energy. So we have to look at what one conserves energy. It would only be this first one because the speeds changing would change the kinetic energy.
During an inelastic collision, the objects deform and they move separately after the collision. The total kinetic energy decreases. During a perfectly inelastic collision, the two objects stick together and their final velocity is the same. The total kinetic energy decreases. During an elastic collision, the objects bounce apart and move separately. There is no change in the total kinetic energy.
There we go. Those are the three. So here's our diagram. We have perfectly inelastic. They're going to move before, they're moving towards each other and then go off together. So they momentum's conserved. For an elastic, the two objects bounce, so afterwards they move separately, and both momentum and kinetic energy are conserved. And inelastic deform, meaning they could both be moving in the same direction, but they're not sticking together. So now, what do you think? Most elastic to most inelastic. Well, the most inelastic, something that would stick together. I mean, two balls of modeling clay are definitely going to stick together. An automobile collision, maybe you'd stick together, maybe not. Or two football players, maybe not. A baseball and glove they'd be sticking together. It stays in the glove. Now, a baseball and bat, the two billiard balls, and two hard rubber toy balls, they're definitely going to be moving afterwards opposite direction, so I'd consider them elastic. Whereas, and these are definite inelastic, perfectly inelastic, the baseball and the modeling clay, and then the football player and the automobile collision could be kind of right in the middle. So here's your chapter review. Okay, and then right now you have the rest of the period to work on your this packet. There's problems D, E, F, and G. But let's I'll let you guys go through and pick out how about you pick out 3? As long as everyone is doing the same one, I'll let you guys as a group pick out 3 from each problem set to do, and you'll have all period tomorrow also to work on these, and then they'll be due on Thursday or Wednesday. They're due on Wednesday, and your labs are due tomorrow, so make sure you have those all printed off in your lab books. I guess it's not a formal one, is it? So you can just work on getting your questions and everything put into your lab book. But you need to have the labs by the end of the period tomorrow. You can work on your packet tomorrow, which are due on Wednesday. I'll see you then.